Awesome. Okay, so now let's turn it over to Michael Hofman here on his talk. He's going to give us a talk on the timing of late Devonian active margin tectonism and sedimentation in the intracratonic Williston Basin. I think Anna kind of covered his bio, but if you weren't paying attention, he's got his PhD from the University of Montana and is now actually an associate research professor at the University of Montana. And he's also worked for ConocoPhillips before coming back to the University of Montana. Before we turn it over to Mike, just a reminder, if you have any questions, just please save them towards the end and write them into the chat box, our little chat window, and then I'll review them and pitch them to Mike at the end of the presentation. But Mike, take it away.
Thank you, Pete, and thank you, Anna. Let me just make sure I got everything figured out here. There you go. All right. So I think we got everything set up here. So I'm here in the RMAG office, which is kind of fun to have a mini in-person event with Andrew and Kathy here, and then everybody else online. First of all, I'm incredibly honored to have received this award. Thank you, Anna, and thanks to APG RMS to giving this award. I think it's according to my title here, this coincidence. It's a coincidence maybe that I received the award in Julie's name. That a person who has contributed so much of her life to better understanding the Williston Basin, and the talk today being around this Williston Basin. So I'm honored to be mentioned and awarded this award in her name. And with that, I'd like to get started here talking about the Devonian a little bit. And I think the audience that we have here today, I figured is a good place to throw out kind of a little bit of a hypothesis that really tests the late Devonian strata in the sense of the intracratonic basin and how the connections exist and what connections exist there. And so the hypothesis I'd like to test here that actually some of the orogenic movements and motions that we observe on the Western continental margin at the time actually recorded in the Williston Basin. And more precisely looking at a core here on the right-hand side from the Williston Basin. Those of you who have worked the Williston Basin, probably very many of you who are on this call here, you have the pronghorn member, which is one of the members of the late Devonian Bakken Formation that is wedged in between the Three Forks Formation and Lower Bakken Shale. And one question that kind of motivated us to think about this and throw out this hypothesis is what causes the deposition and the distribution of this in the basin. And I'm going to show you guys maps, obviously, here in a little bit. Why is it there, and what might control its distribution? And another motivation for it was here really some work we've done with my students like Anna and Clayton in the Southwest Montana, where we observed similar type, and many people before us observed similar type of lithologic successions like the Bakken formations in kind of a shale sandstone formation. But people that have worked the biostratigraphy there and the chronology, turns out there's actually a gap in terms of contemporaneous deposition. So they are more asynchronous deposited rather than actually synchronous, what one would expect by their great lithologic similarity. So keeping these things in mind kind of made me wonder about this hypothesis, what other factors might be driving the deposition other than usually proposed things like rheostatic sea level changes. And so here we go. Before I get started, really what I like to thank is directly more people like Sarah Edwards and Bruce Hart, who directly contributed to this talk, and then SM Energy and Equinor for allowing us to present some of this data. But at the same time, also already mentioned some of my students that have worked over the years with me here on the Devonian and sparked some of the ideas that came out of it that are in part of this talk here today. And then also countless colleagues that I discussed this idea with and got some more motivation to move this forward and think about it. So the way I structured my talk today is just introducing kind of the global late Devonian events, then moving towards Laurentia and talking about the tectonics that happened at the time, just to set the stage. And then showing you some of the data and some of the sedimentary observations and geochemical observations that we see in the Williston Basin itself. And then hopefully I can convince you, at least in my mind, that there might be some good connection between all of these things that control some of the sedimentation that we see in the basin, and then eventually move on to the conclusion. So the late Devonian events, when we get started, one of the big things that happened at Devonian is one of the 5 main mass extinction events that we had throughout the Phanerozoic. As we probably all remember from our 101 class, the most known one, the best known one, of course, is the end Cretaceous extinction, where we see the dinosaurs go extinct. The most significant one is at the end of the Permian, where we see about 95% of the species disappear. But then there's also an extinction in the Devonian that is slightly different in shape. And here on this chart, you just see the geologic time on the x-axis and then the number of species on the y-axis. And instead of having these abrupt drop-offs in species that we see in many of the other mass extinctions, we see a more kind of gradual decline, and then you see these abrupt events towards the end. And really what we're focused on today is near this end of this mass extinction event that occurs. And so if we zoom into these mass extinction events in the Devonian are associated also with often anoxic events that are observed throughout the Devonian. And here's a chart from Becker et al. for the Devonian. And what's marked here in these black bars are these anoxic events that are occurring in the late Devonian, often recognized by either black shales or organic-rich limestones. And so you see they're occurring throughout the Devonian. And then probably the best known one is that Kallwasser event that was recognized in Germany. That's right at the Franian-Famennian boundary. And that coincides with this first major mass extinction event, the significant drop-off. But then in the Famennian, and that's where we're going to spend the rest of the talk in here today, in this Famennian and the latest Devonian, we see a series of other extinction events and anoxic events. They're called the Annulata, Dasberg, and the most famous one, probably the Hagenberg event, and most famous because it is right at the Devonian Carboniferous boundary. And again, associated with this anoxic event is right at the end, just this little bit of a abrupt extinction event, finishing up the Devonian mass extinction that we observed. So zooming in into this Hagenberg event, it was first described in Germany in the Rhinish Massif. And what's the reason I want to show you this quickly is because it has a distinct lithologic characteristic. It's defined by, at the base, by a black shale. It's overlain by a little bit less organic rich shale. And then it transitions or abruptly transitions into a sandstone in the center, and then it's overlain again by a shale. And here on the right-hand side, you'll see an outcrop photograph from Kaiser et al. All these figures are from this publication. You see the shale, these thinly laminated, thin-bedded shales near the bottom, and then near the top, you see the thicker beds coming in. This is your middle sandstone. And this crisis, this Hagenberg crisis slash event, it's pretty well constrained to certain conodont zonations between what's called the presulcata conodont zone and the sulcata conodont zone. And the most significant key species here is actually the Skokali zone. I won't test you on all the names here, and we won't revisit those, but there's some importance to this in terms of the biostratigraphic framework that constrains some of this what we want to test here with our little hypothesis. And so the Devonian Carboniferous boundary then is right above the extinction of this Skokali conodont zone and at the base of this upper shale. Since it has been recognized in Germany, more sections have been seen that seem to be time equivalent, mainly around the Paleotethys here that we see located here on the eastern margin of Baltica, between Gondwana and Baltica. You also see it in Gondwana itself, some other sections that are now located in China and other parts of Asia, as well as in the western part of Laurentia. And this is going to be where we're going to spend most of the day today. The drivers between those lithologic changes that's listed here on this chart at the bottom are fluctuations in sea level. Right at the end of the Devonian, we see a transition between a warm house climate into kind of a little bit of a cold house time, and that has been recognized by the presence of diamictites, in particular in South America, where we see these occurrences and reflecting these Gondwana glaciations. But at the same time, there are few glacial deposits and diamictites that we see also in eastern North America that reflect the glaciation in the Appalachians, in kind of mountain glaciations. And here on the right-hand side is just a nice image of some striated pavement that's now located in the tropics, and so this sits right on top of latest Hofman. And so having this glacial driver, of course, suggests that the controls that we should see, is, at least in part, for this Honingberg, for this latest event, should be potentially be driven from a global, have a global significance and should be reflected in relative time correlative changes that occur. So moving a little bit now into the western part of Laurentia, and getting closer to our Williston Basin, where we're going to focus on today, is in the Williston Basin, this latest Devonian strata, as I pointed out already earlier, has the same kind of tripartite lithology that we observe in the Honingberg event. We have a lower shale, we have a center siltstone and sandstone unit, and then we have it overlain by an upper shale. And here's just a partial core that we see as an example for this lower shale. This middle section highlights part of that middle Bakken siltstone and sandstone unit, heavily bioturbated in this case, and then overlain by this upper shale. And then above that, we see the widespread lodgepole limestone. So very similar lithology at about the same time frame. If we move into central and southwest Montana, what we see, we have a very similar lithology to what we see in the Bakken as well as in the Honingberg, where we have a lower shale, we have a coarser unit in the middle member, and then the upper part in the upper member. And here in southwest Montana, we don't call it the Bakken Formation, we call it the Sappington Formation down there. And there's just an outcrop photo from the Bridger Range in southwest Montana, where it's nicely exposed with the lower shale, that middle coarser unit, and then there's a not very well visible, but there's another dark shale sitting right in here. So we have a very great lithologic similarity between the Bakken and central Montana, or the southwest Montana, and as well as the Honingberg, at least at first glance. So what's striking then, though, is that when people that are concerned about the biostratigraphy and set it in biostratigraphic frameworks, and there was just some recent work done by Hogenkamp et al. That was published in 2018, there seems to be some discrepancies between the lithologic similarity that would suggest maybe contemporaneous deposition and what actually the biostratigraphy tells us. So just looking at some of these sections, this is just a compilation of sections that tend to contain the Honingberg event. And here in this column is the type location in Germany. And you see this red line marks the Devonian Carboniferous boundary. Right at the end of the Devonian, we have almost hidden a little bit here by this red line. We have just before the Devonian Carboniferous boundary, we got the Honingberg sandstone. So we transition from a shale into a sandstone. If we jump across the Appalachians and into the western part of Laurentia, what we see is that in the Sappington Formation, and this is a compilation from Phelps et al. Anna compiled all the different biostratigraphic data that was available at the time. What you see is that your transition from the shale into the sandstone also occurs prior to the Devonian Carboniferous transition, and then you have a hiatus and you go up into the upper shale. more recent work on palynology by DiBasco et al. In the sapphic deformation suggests exactly the same, where the sandstone seems to be predating the Devonian Carboniferous transition. So those have a very similar type of transition to the Hongenberg event, which is different though from what this recent study by Hogenkamp and all is suggesting, is that actually the Middle Bakken and the Williston Basin is post-dating this Devonian Carboniferous boundary. And the Lower Bakken Shale is a continuous succession without the presence of some of these hiatuses that we observe in the southwestern part of Montana, or then even up into the central part in central Alberta, up into Canada in the Exshore Shale. So there seems to be some discrepancy and some difference, some uniqueness about the stratigraphic succession that we observe, in particular from a temporal framework that we observe in the Williston Basin. And one of the big questions is, why is that the case? So now if we zoom in into the western part of North America and look at this paleogeographic map, here are these ice sheets that developed at the latest Devonian. Here are these mountain glaciers along the Appalachians and the Riskin origin at the suture zone between Gondwana and Baltica and Laurentia. And then at the western margin, we see this very straight line in this paleogeographic map from Scotese. That is the suture zone between the Pandalasta Ocean at the time and Laurentia, and that yellow star just marks the position of the Williston Basin. So at the time of the suture zone, what's happened, and probably many of you have heard this and know a lot about it, is the antler-orogeny. Originally, this antler-orogeny has been described in Nevada, and that's where its type section is, where we see a west-dipping subduction zone and the antler accretionary prism thrusting on top of the Roberts Mountain thrust, forming this expression of this suture zone at the time. Once we get, and this event happened in the mid-Devonian to early Mississippian and then continued up into the Permian. And if we go north from Nevada, we start actually tapering out, and the evidence for this tectonic event, at least originally, is somewhat disappearing and obscure. And so this is just a compilation from one of the earlier studies from Speed and Sleep in '82. So that's kind of the traditional antler margin that many of us have in our head. And then over the last decade, there's been a lot more work done on this Devonian boundary in the Devonian margin in Laurentia. And what occurs there is, instead of just having this westward dipping subduction zone that's present in the antler orogeny, we see actually an eastward dipping subduction zone that's obliquely bringing the Pandalasta plate or Pandalasta Ocean underneath the Laurentian plate. And this is mainly constrained by detrital zircon work that was done, where many of the detrital zircons, or several of the detrital zircons found in some of these terrains that are now located in southern Canada or even further south along the western margin of the US, actually contain detrital zircons that were derived from northern Canada. So there's some transport that is along the western margin of North America during the Devonian, bringing these terrains not straight into the Laurentian margin, but actually transporting them parallel to it, and we get more of an oblique subduction. What is important about this model of this oblique subduction, which has been proposed here from Colburn and Nelson in 2009 and has been confirmed from several studies since, is that your plate motion projects directly from the Pandalasta Ocean, projects stresses directly into the Williston Basin at the location of the Kootenay Arc region in southern British Columbia, rather than the antler orogen projecting it into the Williston Basin, or what we see in central Idaho. So that is important then for our story to think about, because any contemporaneous events that happened should be constrained to what we see in the Kootenay Arc region in southern British Columbia, rather than what we see further south in Idaho and Nevada. Another thing is with recent modeling study, and here's a study from Balash et al. In 2021, is that in these oblique situations, with these oblique motions of these plates subducting under the Laurentian plate, this is just a model, not specifically for this Laurentian plate, but just a general model, is that we see with an increase in subduction velocity along these subduction zones, we also see an increase in upper plate extension. And with this eastward subduction of the pendular plate underneath Laurentia, of course, Laurentia becomes our upper plate rather than when we just think about the traditional antler-orogeny, where the Laurentian plate actually would have been the lower plate. So keeping this in mind for our later interpretation of and testing of our hypothesis, these different modeling studies. So moving into the Williston Basin, our study area is kind of located in the center part, and white is the outline of the Williston Basin. It's the same shape on both of these maps that we see. The Williston Basin sits on a triple junction, if you want, of several Archean provinces, namely Superior Province to the east, and then the Wyoming to the southwest, and the Medicine Hat Province to the northeast. And they're separated by these Paleoproterozoic suture zones that are known in Montana, for example, by the occurrence of the Great Falls Shear Zone that trends all the way across the state, and then the Trans-Hudson origin going in kind of a more northwest-southeast direction underneath the Williston Basin. And the reflection of these Paleoproterozoic suture zones and older lineaments can be also inferred from the presence of some of the known lineaments in the basin that are seen, like the Weldon-Brockton-Freud fault zone that is trending exactly the same trend as the Great Falls Shear Zone, so the Paleoproterozoic suture zone between the Medicine Hat and the Wyoming province, and then other trends like the Goose Lake trend and the Antelope anticline that have more the direction that we see with the Trans-Hudson origin. So the similarity of these trends between the Precambrian basement and those known structural elements is pretty striking and pretty well known. So what happened in the Williston Basin at the time? So if we zoom into the lower Bakken Shale, and it's just a compilation from Gasworth and Maurer that shows the latest Devonian strata and naming of it. So we have the Pronghorn is the lowest member of the Bakken, and the lower Bakken Shale of the second lowest member, and they're going to be the focus of our study here. And so we focusing on the center part of the basin. We have looked at about 1,000 well logs at the time, constrained to about a little over 20 cores that we looked at in this area. Many of them we had also petrographic data, and about half of the cores also had elemental data from XRF in the study area. And the cores are highlighted in yellow here on this map. The general stratigraphy that we observe is well known to the people working in the Williston Basin, of course. We have these kind of faintly laminated to structuralist looking to sometimes laminated, very dark black to dark gray, dark brown mudstones that form the lower Bakken Shale. And then often it's embedded in certain cycles, in certain intervals, by these little coarser units, these siltstones that are nicely laminated here in the photo example to the right. And in this compilation here from Hogenkamp and Pocknell in this strat section, you see that these are potentially forming these little parrot sequences within the lower Bakken Shale, the way they stack those facies. In difference to that, the pronghorn facies is much more bioturbated and much coarser. So here's a nice example of the pronghorn, heavily bioturbated siltstones and sandstones that we see in there. Here to the right is a nice example of a more mud-rich unit, but again, very heavily bioturbated, kind of chocolate brown, heavily bioturbated mudstone, often calcareous. Sometimes you also see allochems in there. So very, very different in facies from the lower Bakken Shale. And of course, this is really well known and has been studied for a long, long time. One thing what we notice in our study area is that in some instances, what we call the pronghorn member in the lower Bakken Shale, the pronghorn member is actually very similar to the lower Bakken Shale. And so here we see some photomicrographs, and here's a scale bar of about 100 micron on these, where you see they have great fabric similarity between these two. So in this upper part, you see these laminations and these little elongated features are Tasmanides cysts that are aligned with your lamination of your shales, and you get a very different, similar fabric in the pronghorn shale. And the pronghorn sample, this pH sample, and that LBS sample, in this case, are only about 10 feet apart from each other. So you wonder why we call it the pronghorn versus the lower Bakken shale. And with this, actually, we relied a lot on the geochemical data that we had available in our XRF data. And what you see here is that right between those two examples that I show you here, these petrographic examples, there's a distinct shift in your elemental values. And what's listed here in your diamonds is your vanadium. What you see in your square boxes is vanadium-chromium ratio. And then the triangles are molybdenums, and these are all enrichment factors for these particular elements. And what you see, there's a distinct jump and distinct shift from lower values, lower enrichment factors to higher enrichment factors, right where I've drawn this line from green to blue. And so in blue here are all our lower Bakken shale samples, and in green are our pronghorn samples. And so this change in geochemistry made us think about that there might be actually a stratigraphic boundary separating these otherwise very similar looking facies from each other, and maybe one being related to the pronghorn and one being actually related to the lower Bakken shale. If we look at more samples here, and this is just a compilation of all of our samples, but what jumps out is that when we look at the concentration of molybdenum and zirconium as two elements, is that the coarser grain pronghorn facie is the one that's really well known and has been mapped across the basin quite often. You see it clusters in its own little region with a little higher zirconium values and much lower molybdenum concentrations. What's striking, so here is, again, in green is all the pronghorn samples, and in blue are all the lower Bakken shale samples, is that the pronghorn, the finer grain pronghorn samples, the one that have a much greater facie similarity to the lower Bakken shale, still cluster away from the lower Bakken shale samples. So they're distinctly different in their geochemical composition, but similar to what I just showed you previously. And when we look at just some other ratios here in your geochemical signal, we see exactly the same, where the pronghorn just clusters, has its own concentration, clusters around its own concentration compared to the lower Bakken shale. So distinctly different. But I'll show you one more plot of these geochemical data, of these elemental data. These are just some box and whisker plots. Vanadium and molybdenum we already looked at. The nickel and uranium are yet some other ones. And if we plot it in this way, they're discrete boxes around these different facies. So the lower Bakken shale, distinctly different from the pronghorn, usually enriched in all these redox elements, rather than the pronghorn that seems to be depleted. And in the pronghorn, this contains all the samples, including these well-known bioturbated pronghorn samples, as well as these more organic-rich, in this case it's still bioturbated, but organic-rich samples, as well as the one that I showed you with that photomicrograph that has a very great facie similarity between the lower Bakken shale and the pronghorn. So the geochemical evidence made us think about as a driver and picking maybe some of the surfaces new. What's interesting when we then looked at the ones where we find all the cores, wherever we observe a change in our geochemical pattern, we actually had the presence of a bioclastic lag deposit that's composed mainly of different allochems, phosphatic, silicious, and calcareous allochems that are concentrated along a thin bed, always where we observe this change in geochemical values. And what's important about this is where we see this type of bioclastic lag occurring in an area where the Three Forks formation is directly overlain by the lower Bakken shale, this lag deposit becomes really thick, several centimeters in some instances, and is coarse as grained. While if we go into areas where we have the pronghorn present, either in its distinct facies or in the facies that can only be separated by the geochemical pattern, we get successively thinner and thinner the further we go into what we think about little subbasins. So the thicker the pronghorn becomes, and then the beds, they become thinner, but then also become finer grained. And here we're just looking at a cross section that runs from north to south, north to the left and south to the east, that we see in there. So we have an evidence from our sedimentary record as well that seems to suggest that some event is happening right at this boundary and is driving part of these geochemical changes that will occur, that we see even in areas where otherwise the facial similarity is pretty great between the pronghorn and the lower Bakken shale. So that made us repick on our log data, made us repick our tops a little bit, where originally we might have picked them right down here at the first inflection of the for example, on this gamma ray log, or the density and porosity logs that we see. And after integrating the geochemical data, and you see again here the same patterns used for our enrichment factors on vanadium and molybdenum, is where we see this significant jump. They're usually located a little further up in the section where the slope starts flattening out again. And so we ended up picking our geochemical tops from our logs just further up in the section. By doing so, we then ended up with these isopack maps for the pronghorn and the lower Bakken shale that separate the pronghorn into distinct subbasins. Here, the one to the southwest, of course, is very well known. This is where the pronghorn has been producing and studied for many decades. But here to the north, there are some subbasins developing. These are the areas that have very great facial similarity between the lower Bakken shale and the pronghorn. But if you separate it by our geochemical pattern, we start creating these little subbasins that are separated by these straight lineaments or lines that trend in either northeast, southwest direction or in a northwest, southeast direction, respectively. When we go up into the lower Bakken shale, we lose these trends and we get more kind of one significant depositional center, kind of more towards the eastern part of our study area, but we lose these lineaments and these trends that we observe in the pronghorn formation. Just one last slide here, just to show you why we think this might actually be depositionally driven. In addition to what we see with these facies changes within this bioclastic lag, just looking at the subbasin to the north and looking at a few cores, what you see is that not just is the pronghorn thickening, and here these red diamonds are the pronghorn, and we're looking at vanadium chromium values here. Not just is the pronghorn thickening towards that inferred basin center, but what you also see is that the vanadium chromium values change from a lower ratio to a higher ratio going towards that center basin. And you don't see any of these changes occurring in the lower Bakken shale sample, where the vanadium chromium values stay consistently high at around 10. So that seems to be there's potentially some depositional control on this distribution of your geochemical ratios that you observe. So if we believe that we see all these changes and that they are driven by deposition, and I have to think about what might cause this actually deposition to occur. And so going back to the initial slides that I showed you about some of the events and the basins that we have, is when we look at the lineaments, these northwest, southeast lineaments trending across the basin and the pronghorn, so these areas of low deposition, and then comparing it also to this northeast, southwest trend, they perfectly align with these earlier mentioned lineaments that we observe, like the Weldon-Brockton-Freud fault zone and the Antelope Anticline Goose Lake trend, respectively. So we have these crust lineaments, these lineaments that are well known, seem to be aligning with what we think are subbasin margins that occurred through time. And because we think that these are depositional basins based on the data we have to think of what causes some of these lineaments potentially to move at the time. And so there's been recent work done on thinking about what controls subsidence in intracratonic basins. And what was very striking to me, and we kind of developed this idea about the lineaments and they controlling deposition way before I've even seen this study. And what was striking in this particular modeling study, interestingly, is that apparently the reactivation of these lineaments within intracratonic basins, so pre-existing lineaments in intracratonic basins, is dependent on the presence of far-field tectonic effects. So you have to have some far-field stresses that are related to basin marching conditions that actually reactivate these basins in the intracratonic basins. When we just look at thermally dominated systems or sediment flux dominated systems, those faults that are highlighted here in these straight lines are inactive, and we got a more consistent and homogeneous subsidence in the basin. So that, of course, made me very curious to think about, well, if that is the driver, how does this all connect to what we might see in this Western continental margin? And this goes back to this figure I showed you earlier, just to remind you. So the stresses we really are concerned about, given this oblique subduction into the basin, are the ones related in this Okanagan region in southern British Columbia that project into the Williston Basin. And we might drive what we see, these far-field effects, like our extension based on different subduction velocities. So looking at this Okanagan region in south British Columbia, and here's the Canadian-US border on this particular map. What is interesting is that at the time of the pronghorn deposition, so the pronghorn was deposited at as far as at least at recent biostratigraphic charts and chronostratigraphic charts, around 366, 367, 365 million years is kind of the timing of the pronghorn deposition. If we look at the record from the Okanagan region, we see in plutonic activity and plutons intruding into the area at exactly the same time, about 366 million years, 365 million years. There's some ash deposits dated in the Exshaw Formation in the Western Canadian Basin, and then just shortly thereafter, there's another intrusion dated in the Ice River complex here in the Kootenay Arc region. What's important about this Pluton, in particular, this one in the Shuswap Lake area, the 366 million year old one and the 354 million year old one, is that they don't just intrude into the craton, North American craton, but they intruding into both the Okanagan terrain as well as the craton. So it means that that suture zone, that docking of the terrain at the time already ceased, and we already had the Okanagan docked onto the North American continent for those intrusions to intrude. Just earlier in about 370 million years, there are some reports of active deformation in the Kootenay Arc region. So that suggests that sometimes between 370 million years and 366 million years, we might cease the docking. So we docked the Okanagan terrain, we ceased the docking, we got intrusions that came in. And of course, with intrusions, we need the presence then of subduction to actually get the magma we need to intrude into the crust. So that coincidence of timings or contemporaneous timing of events made us think about our model that we bring forward here, is where we think what we see is we had this docking of the Okanagan terrain along the western margin of Laurentia, and then the initiation of a subduction zone along the western margin, this oblique subduction. During this time, because of the subduction activity, we had the far-field tectonic dominated or far-field tectonic influence on the Williston Basin and an overall extensional plate. Remember, when we start subducting under the upper plate becomes extensional, and this extensional regime then started the reactivation of these northwest-southeast trending lineaments as well as the northeast-southwest trending lineaments, causing the fragmentation of our basin into these subbasins. Once subduction is ongoing, this extension becomes more widespread, affecting the whole continent, upper plate, resulting in the flooding of the shelf and the subsidence of the Williston Basin in particular. With that higher subsidence, then eventually we also transition into a more sediment flux dominated system that then, of course, has its height at the transition into the middle Bakken, which we're not looking at today, but where we get a much higher sediment flux into the basin and more suggesting a more coherent and consistent subsidence into the basin. that we see, and this would be kind of this lower Bakken shale pattern here. So, in going back to our hypothesis, just to start wrapping it up here, before you can throw eggs and tomatoes at me with this suggestion, we think, we in our hypothesis here that the Antler-Orogeny actually might be having a record we can see a record of the Antler-Orogeny in the late Devonian strata. We do think that there is this control that is present, in particular in the controlling the deposition of the pronghorn member, and moving forward also, looking into how does this transition really, how does this transition in our tectonic regime really reflect some of the sedimentation that we see in southwest Montana? Is this hiatus, for example, can this be explained by the southward migration of our tectonic front along the western North American margin, and then moving here kind of from this deformation regime into a more subsidence regime, similar to what we suggest we see in the pronghorn member to the lower Bakken shale. So before I wrap up, just a couple of other things that I came across in recent publications that I think are interesting food for thought. Ronemas et al. Earlier this year published a paper where they looked at detrital data from the late Devonian, including the sapping formation in southwest Montana, and they described or found northern Appalachian detrital zircons in the sediments of the Sappington Formation. And their model, they're thinking about maybe some type of an overfill, so fill and spill type system from the basin into the Sappington Basin. If we believe that in our model that we have these reactivations of those structural lineaments in the Bakken Basin, we actually create potential sediment bypass zones that allow for more direct transport from the Appalachians into southwest Montana without having to fill the basin completely and spilling it over. So one thing we would be very interested to investigate further, whether that model could potentially explain these findings. Another thing is, of course, the weird, not really weird, but interesting observations of production differences that are observed in the Williston Basin. Here's Nording's compilation of the percentile rank production in the Williston Basin, where we see these curious northwest-southeast trending lineaments of low production, and again along here the Walton-Brockton-Freud fault zone in more northeast-southwest direction. A similar finding from a more recent study from Steve Sonnenberg, who also sees the similar trends in these production data. But what's really curious about this study from Steve is that near the top of the Divide County here, right at the border to Canada, we see this height of production rates, this little curious height of production that coincides perfectly with the presence of this pronghorn subbasin. So the question is, what controls do these potential Devonian structures have on these production maps that we see here, if we believe that these are true controls on sedimentation at the time? And then zooming in at last here at the Cooley field where the star is located, a study last year from Cutry and Burberry showed that they suggested that some high production rates in the Cooley field can be explained by the presence of kind of step over faulting that are related to the Walton-Brockton-Freud fault zone. In this case, these authors suggested that this is related to the Laramide orogeny. One question I'd like to ask here is, could that potentially be much older and related to the Antler orogeny initiated by it, if we believe that there is this long far-field effect that had quite significant control on the deposition during the latest Devonian. So with this, I'd really like to wrap it up. Thinking that here in summary, you can read it. We really can link the latest Devonian fill history in the Williston Basin to what we see in the Antler orogeny. That the main control here comes really from that Kootenai arc region, one we want to think about when we think about the Williston Basin and what controls it. And more importantly, also at the very end here, this last point that I'd like to point out is there actually are these intracratonic sedimentary records that we see undervalued in actually constraining some of the basin margin positions and constraining the movement on these basin margin positions, in particular in areas like the Antler orogeny and the late Devonian orogeny, where we have the signal obscured by subsequent event like the Laramide orogeny, or even completely subducted in some instances around the world. So can we use that? Can we use this intracratonic record more efficiently to constrain some of these events, not just in the Williston Basin but around the world? So with that, I thank you for your attention. And like I said, this is more a hypothesis I'm throwing out there to this audience. And any comments, suggestions, poking holes into the theory would be great. Looking forward to it. Thank you.
Thank you, Michael. That was a great talk. That was really interesting. If anybody has any questions, now's your chance to load them into the chat window for us to ask Mike. We have one question here, Mike, from Ted. Your upper... Can you see the questions? There, your upper pronghorn.
We got some trouble here with the speaker. Hold on one second. All right, let's try that again. Any questions, anybody?
Yes, you have one question regarding the upper pronghorn. Sounds like the lower Bakken silt that was defined much earlier by Cantor and Skinner and many others. Is that true?
Well, that's a good question. I mean, there's some. I mean, obviously the pronghorn and the Spanish stance and whatever name you want to give to them has been studied in great detail over the years, and has been defined and of course produced also in the basin itself. Has been defined in many regions. There's still a lack in parts of the Conadon data to really separate those two units, the pronghorn and the lower Bakken shale in itself. And when you look at the latest compilation from Hogenkamp and Pocknell et al., they actually transition more or less from the pronghorn into the lower Bakken shale that we see there. So can it be related to actually directly related to the lower Bakken shale? Yeah, there's a possibility from biostratigraphic data. Like I said, from that sedimentary evidence, in particular, the presence of this lag deposit that always seems to be separating the prong, what we define as the pronghorn in across the basin, has been defined as the pronghorn before by many other authors. The change in the sedimentary pattern of this lag deposit seems to suggest that there is actually a time gap between those two that seems to maybe stratigraphically separate those two. So, Ted, your question is a very good one, and I don't really have a straightforward answer on it without having more biostratigraphic data to really either genetically link those to each other or separate them, what our sedimentary evidence seems to suggest.
Yeah, but your XRF data definitely suggests that they seem to be different, though.
That's right.
Yeah. So
they seem to be different chemically, but what is exactly the time gap that exists between the two? I don't have an answer to that.
Sure. Yeah. What analytical technique did you use to determine the elemental concentrations? And what was the vertical sample interval?
Okay, we used the XRF data, and we used the handheld XRF for this particular, that was calibrated against several standards that we had in there. And the sample interval, we started out with half-foot intervals, and then we went down to pretty much 0.1 foot scale. So we pretty tight on intervals where we found, once we started finding these individual intervals and these lag deposits, we pretty much went on a centimeter scale across these boundaries.
That's pretty tight.
Yeah.
Well, it's 1 o'clock, and I've got to jump off to run to something. And I think that's it for questions. But Michael, thank you very much. Congratulations on your RMS award.
Thank you.
and look forward to seeing you around, hopefully in the near future.
Yeah, thank you. Yeah, and if there's additional questions that people want to ask, please email me or contact me. Otherwise, I'm more than happy to have more discussions about this. Like I said, this is a hypothesis where I'd like to get a lot of feedback as well.
Okay. Thank you, Michael.
Thank you. Thank you.
Bye-bye. Bye-bye.